explain two things. Welcome back, of course. I still want to explain two things, namely, how can we represent now interesting game information in first-order logic, and how can we translate it, what does it mean to translate it back to propositional logic? So now we're sort of getting at the meat of the lecture. Let's start with the question of representing knowledge about decision problems in first-order logic, in particular this game. So what do we need to do? We need to identify the task that we want to solve, and we want to write it down as a strategy in first-order logic. There are usually different things. We can have knowledge about the environment, the generic knowledge about the environment. But we also have specific information about the state we are in and the state we could move to given a certain decision that we take. And then in our case, it's now translating the knowledge base into propositional logic and closed normal form, and we're going to practice this now, given some examples. So I showed you this slide, the knowledge engineering task, and this is really a complex task in practice. So we have a master course which is called Knowledge Engineering, where you really try to understand how can you extract the knowledge from experts and implement it in some logical formalism. Here we do sort of quick and dirty, identify the task, assemble the relevant knowledge, and I've had you practice the Schnapsen game, so we should all understand enough of the Schnapsen game to be able to represent most of it. We have to now encode the general knowledge about the domain, and we will do that very selectively, only for the strategy at hand. Then we encode the description of the specific problem instance and pose the query as an inference problem. So I've thought of some strategies, and some of them are completely stupid. Some of them are not. And this is really something where you should, at the end of this week, add your own strategy. I want to show you the play Jack strategy, maybe a little bit about the play cheap, and I also have one slide about the play Trump wedding, and that should give you some idea of what I think we can do with these formalisms in order to help us, our agents, to make a decision. So what is the play Jack strategy? It's simply going through all your 5 cards that you have at hand and check whether it's a Jack, and if it's a Jack, you play it. Yeah? So it's, I don't want to lose any points, so I play my cheapest card, it's a Jack, play it. And one way of doing it would be to use your programming logic. So of course, you can also look in the logic of your bot, and you can look for, give me all the cards, what is their value, card value, and then play the Jack. But we now want to have a declarative definition of a strategy. And this declarative strategy I call play Jack, and it's just play the card whenever it's a Jack. And then you're done. Basically, you have made your move. So it's a very simple online decision procedure. You just check whether the card adheres to some criteria, and in this case, the criterion is simply, is it a Jack or not? And so what does it mean? I want my knowledge base that I write to to check for entailment of my knowledge base with the formula play Jack of the card that I'm checking for. And I want this to be true if the card X is a Jack, and I want it to be false if it's not a Jack. So this already gives me the sort of the definition of what I want to check for, and it's, as I said, it is completely trivial. The one thing I want to check is that the information I have that everything adheres to the play Jack strategy. So that's this bit here, if and only if it has the property of being a Jack. Really sort of more simple can't be. And all I need to know, add to my knowledge base then, is the fact that number 4 has the property of being a Jack, number 9 has the property of being a Jack, number 14 has the property of being a Jack, and number 19 has a property of being a Jack. And these 4 numbers, of course, come from the implementation of the game engine. I don't know whether you had a look at the code, But remember that, or if you either you remember or I tell you now, all the cards are numbered from 0 to 19, and number 0 is an ace, number of heart, I think. There is a table somewhere on the README. Huh? So you start from clubs, and you start from club ace, then come clubs 10, clubs king, clubs queen, and then clubs jack. So number 4, card number 4, because you start at 0, card number 4 is a jack. And then you go on to the next color so that the last one is again a jack. So if you go to the README file for the engine, you will see this representation. And basically what I do is I do it now the other way around. I assign the values to each of the identifiers of the cards in the game from the game engine. So I tell my logical knowledge base that if I encounter the card with the index 4, it's a jack. And the card with the number 9 is a jack, card with index 14 is a jack, and 19 is a jack. So this is the information about the game. And all I now need to do is when I have a card on my hand, card with the index number 5, I have to add it in a negated form to my knowledge base to check for satisfiability. As I said, it's a proof by refutation. So I want to show whether play jack of 5 is entailed by the knowledge base. And as you can see, easily it is not, because the only thing we know in our knowledge base is that 4 is a jack, 9 is a jack, 14 is a jack, and 19 is a jack, and 5 is not. And if we encounter the 4, then the answer will be yes. The only thing is now that this is a first order formula. So if we enter this into our propositional logic engine, it will not do anything, it will fail. So what you basically have to do is to encode now all the atomic information that you could have in your proposition, in your first order logic, into some propositional statements. So basically we say the 4 has the property of being a jack if and only if the proposition jack 4, and that's a new proposition, is true. Yeah? So I translate this first order statement of jack of 4, which is a property of 4, into a propositional statement. And I just have to add all of these to my propositional knowledge base to have the same information. Don't worry, you don't have to read this. It just says jack number. The more difficult thing, and I tried to write it so that you can read it now, is that we have to translate this formula into an equivalent propositional logic formula. And how do you do this? Basically, there are two things. Of course, we can, and now this is a thinking process that we have to do. We have to show that we have play jack of x implies jack of x. So this is still in first order logic, and the other way around is jack of x implies play jack of x. Yeah, so it's the two directions of my equivalence. And now basically all we have to do is to write down this statement for all possible values of x that x could take. And we have 20 of those. So we have to write 40 formulae to write this down in propositional logic. So basically what we have to write down is that if x is a 1, we get this play jack 1 propositional variable to be true, implies jack 1, which is again a propositional variable as our knowledge base axioms. And I also have to do this for the second one, so we have jack 1 implies pj1, and those are not in closed normal form yet, So we can transform them into not pj1 or jack of jack 1, and the other way around is not jack 1 implies pj1, and that gives me the first two of these axioms. And I need to do this now 20 times for all the values of x. So for this very simple statement, I've now translated this into 40 simple statements in propositional logic that are equivalent in the sense that you can derive the same things from the propositional knowledge base as you could before in the first order one. And here I've written down the abbreviations that I've here as well. So it's this for variable 1, but you also have to do it for variable 2 and for variable 3 up to or 0 to 19. And then what you have to do to this propositional knowledge base is to add the statement, suppose I want to check whether my card playing the card 7 adheres to the play jack strategy. I just have to add the formula play jack 7 in a negated form to the knowledge base and check whether it is satisfiable or not. And if it is satisfiable, I can't show anything. And if it's a contradiction, if it's inconsistent, then I know that my entailment is true. So basically, it becomes inconsistent when I add pj4, for example, negated to it, because then I know there is a contradiction. And my reasoner will show that. And basically, what will be in the worksheet or in the example board that we give you is exactly this. So you have to define clauses J4, J9, J14, J19. These are the propositional statements to say that 4 is a jack, 9 is a jack, and so forth. And then we have the clauses that we have to add that if J1, then Pj1, and if Pj1, then J1. So that's the two directions of the implication. So that's what I've written down here. And we have to do it for all the variables. So you get a long list of those. This might seem sort of strangely complicated to do it that way. But the point is, of course, that there is a way of doing this automatically. So you go from this formula here, you go to, from this formula here, you go to a propositional formula that is equivalent, and you automate this. So you model this, and you let it automatically be translated into propositional logic. So this was a sort of stupid example, because we could have checked for Jack 4 in the first place. But it might become more interesting if we say, let us define qualitatively cheap card, what cheap cards are. So the play cheap strategy that we can implement easily in this, or represent easily in this formalism, is to say X plays cheap if it's a jack, a queen, or a king. Yeah? And then we do exactly the same. We have the game information that 4 is a jack, 9 is a jack, 14 is a jack, 5 is a queen, and so forth. So we have to give it all the information that it needs to do these checkings, but then we can apply the same. We just need to do this translation into propositional logic. And then we have to do the translation in closed normal form, which I think is not so sure whether it comes out automatically in closed normal form. But it makes sense to sort of play around with this a little bit and try it out whether it works or not. In a way, there are similar things done in the implementation of the bullybot. But the bullybot implements this strategy in an explicit coding environment. So it's difficult to choose a strategy and to also sort of define concepts on a higher level. Because what I've done here is a little bit sort of ugly. I say Jack X or Queen X or King X. What I should have done is to define, to write one axiom in first order logic that says cheap. So for all x, cheap of x, if and only if jack of x or queen of x. So I define once and for all what I mean by cheap. And I might have more of those, high or cheap or expensive and so forth. And in this way, you can model your strategy on a more sort of conceptual level without going down to this nitty-gritty detail of your representation. The next step will always be how to translate this back into propositional logic. One last strategy that I want to think of is a trump wedding. So you always play, if you have a queen and a king from the trump color, you always play it first. So basically what you want to do is you want to check through your cards, is there any card that is the queen? The card is also trump. And I also have in my possession the king of the same color. I know that the game engine allows you to do this in a slightly easier way, so maybe it's not worth implementing this strategy, but still it's possible. So what I said was, it has to be a queen, it has to be a trump, and there needs to exist another card which has the same color, which is the king, and which is in my possession. So it has to be my cards. Yeah? And then all I need to do is somehow implement the predicate or represent the predicate same color. So it's either they're both clubs, or they're both diamonds, or they're both hearts, or they're both spades. And then I need to sort of tell my knowledge base which are my cards that I have on my hand. And I have to tell it which are the card values. So this is all generic game knowledge that you can put into the system once and for all, or at least translate once and for all, and then load into your knowledge base in order to do the reasoning. And then the only thing you need to do is basically check whether your card that you play adheres to the strategy of a trump wedding first, and it will just translate this into propositional logic, do the reasoning, check whether it's a trump wedding, and if it is, you can play the game. And in this way, you can sort of try to implement your own strategy that you would apply for Schnapsen in this explicit, declarative way. So now what we need for this to work technically is that we translate this into propositional logic. And basically, this is a standard procedure for reasoning over first order logic formula if you know that the domain is finite. And basically, the reason why this works is that you can substitute a variable by one of the constants, and the formula is still entailed. So in that sense, it's entailment preserving for any of the variables that you would replace by a ground term. And a ground term in this sense, in our case, is mostly the constants, because we don't have no user function symbol at the moment. So let's look at this example from the slides from yesterday. If you have an axiom saying for all kings and greedy implies evil of x, then you just have to multiply it by all the possible groundings, but all the possible instantiations. So if we have a domain that has John, Richard, but in principle also, if we have a function, then we also, if we have a full-blown first-order logic language which uses functions, then you also have to do the grounding of your axioms with these the grounded functions. This doesn't apply in our case, luckily, because I don't think we have any function, at least in the simple examples that I could come up with. But maybe if you have good ideas to apply functions, then that might also be something you have to take into account. So basically, this is for universal quantification. You just have to write the same axiom several times with the different instances and then you get an equivalence preserving, an attainment preserving rewrite of your knowledge base. In the existential case, there are two different ways of looking at it. If you have don't know the size of your domain, if you have an open domain, you can still do such a propositionalization, and that is by choosing a possible, just a new object that you can make your example for an existential quantification, which is called a Skolem constant. So that's this Skolemization of first order reasoning. In our case, this is not necessary because we have a closed world assumption where we know all the 20 cards. So if you have an existential quantifier, you only need to take one of the 20 cards as a possibility. So here's an example. If you have your knowledge base in first order logic, which is similar to what we have done, like this universal quantification statement, and you have some instantiated formula, you know that our domain has John and Richard, and you just have to apply all the elements in your knowledge base and the ground terms and apply them to your universally quantified formula. So in this case, this is John. If John is a king and greedy is of John, then John is also evil, and Richard, for Richard, holds the same. And then basically what these things become, they are not predicate symbols anymore, but they now become propositional symbols. So you could leave out, I always leave out the brackets to make sure that nobody understands them, nobody sees them as predicates, but they are propositions now. They are statements that are now interpreted as true. Yeah, so yes, if this is true, if John is king. This is one proposition. So these are as is written down here, the propositionalized symbols are now King John, Greedy John, and to be sure that I understand the difference, I usually leave out the brackets to make it more readable. And then there is this sort of general result is that every first order logic knowledge base can be propositionalized as to preserve attainment. And the ground sentence is entailed by this new knowledge base if it is entailed by the original knowledge base. The problem is that with function symbols, we might have infinitely many ground terms. So our propositionalization might have to work on infinitely many terms now. So we might get an infinite knowledge base in propositional logic. And obviously, this doesn't work. So here, we fail. And this is the reason why we can do this. We have a complete translation from first order to propositional logic, but the first order formula might end up in an infinite knowledge base, which explains the undecidability, because otherwise we would have presented a decidable algorithm for first order logic. Yeah, so here's the thing that I started out with. We said in the beginning, first order logic cannot solve all the problems. Then we say all the problems can be written down from first order logic in propositional logic, and then they sort of can be solved. So that would have been a contradiction. But the problem is that we cannot really translate everything from first order logic in propositional logic, finite propositional logic knowledge bases, because we might have infinitely many axioms, and then we can't use propositional logic reasoning anymore, and then propositional logic with infinitely many axioms in our knowledge base also is undecidable or semi-decidable. So in a way, we can't solve the problem of undecidability of first order logic by this propositionalization, but it helps us in this concrete case where we don't have these sort of symbols the function that we have to translate as well. That was a sort of way back to the theory that I was talking about. And basically, this is what I just said, that Turing showed with the similar result in the same year by Church that attainment for first order logic is semi-decidable. So we can, in principle, come up with an algorithm that propositionalizes all the first order logics up to a certain length, but if there are loops and we have to create infinitely many of these knowledge bases, then we cannot apply this algorithm to solve the first order logic problems. And this is why we have this theorem at the end that, okay, we can find all the things that are entailed, but we cannot decide whether something is not entailed, because our algorithm that to decide entailment could run forever. Okay, so here's another example for a strategy. Oh, I think I've done that. So the thing that you should do this week is somehow to understand the way that you can represent knowledge in this first order logic and how to translate this into propositional logic via propositionalization, where the formulas that you come up with are in clause normal form, so this simple formalism that we can then put in the propositional solver that we provide. And there will be an example in the one bot that we provide that is published today. And the idea is, of course, can you come up with better bots? Because I'm sure the ones that I've thought about here, they are absolutely not complex enough to win anything interesting. I mean, they will be on the level of the bullybot. Look at the bullybot, what the bullybot does, and try to improve it with some more strategy that you might have already developed when you played the game. My prediction is that we will not be able to come up with strategies that win against the learning games, but in principle I'm pretty confident that we could get some reasonable behavior, but then we really need reasonably good strategies. There's one thing I want to add before I move on to the next theme, is that the way that the bot that we provide is implemented is that it only does one check for all the sets of cards. So we go through all these 5 cards that you have, and you check for one strategy. If the strategy is true, you play the card. If the strategy is not true, then you just go to the next card. And if none of them does the strategy, you choose a random card to return. But obviously what you would like to do is sort of stack your strategy. So you want to say, okay, if I have the trump queen for a marriage, I want to marry this strategy first. If this one doesn't work, I check for another strategy, and so forth. And you could sort of implement these strategies in one logical formalism, but that might be a bit painful. So you can also sort of extend the logic of the knowledge bot so that it does loops, not only of the deck of cards once, but that it does it according to the strategy that you want to implement. Yeah? So I hope that we get this going. We do this for the first time this year, this knowledge-based approach. So it might be a bit less smooth than the first week. Let's see how we get there, and I will give you more information about this during the course of today, with the example of the worksheet and the most simple bot to start with. So that was the point I made in between. Yes, that's nice and pretty, but all the strategies that I've shown you are already implemented in the knowledge, in the bullybot, I think, or more or less. So why on earth do we need to do all this logic stuff? And I think the answer is that if you, it's sort of the classical answer that you can build up a stock of declarative knowledge about games. So we can, for example, compare strategies on a far higher level by all contributing to one knowledge base and reusing the knowledge if it is represented in this higher representation, such as in the first order logic statements. You can combine strategies more easily in principle or properties of cards. So you can say, I want a cheap card that is not trump. I want a cheap card that I want to play a cheap card, but one where the wedding is impossible. And you can all state this on a sort of human level, which will help us to build a more intelligent agent. Is the theory. I'm not sure whether it really will work. The one thing is you can collect the knowledge in some declarative way. The other thing is you can reuse this knowledge from others. And the third thing is that it's far more far less prone to errors. So maybe in our case, we need to do some translation by hand, and that's obviously painful and maybe it creates mistakes. But when you have, for example, a translation tool or in your model in first order logic, you agree on the model, you can check the axiom of your strategy, for example, you know that it is correct. While if you look at the implementation of the bullybot, for example, it becomes very easy to sort of add mistakes in the logic, and it's far more difficult to share also these kind of codes. So that's the reason why I think that it makes sense to look at a more explicit declarative representation formalism. So this was all I wanted to say about the modeling of explicit game knowledge for our games, for decision making in general. It's one approach. There are many other approaches to do this, but this is the one approach which I think is feasible for us now to do in class in the practical exercises and achieve for the final project. So I want to close the class today, and I will probably finish a little bit earlier than normal, talking about the final project, because you're now halfway through the technical ideas, and you have some part, I believe, implemented. So you should have a min-max algorithm on phase 2 running, and maybe you had a look at the RDeep also that works on phase 1. So some random sampling on Monte Carlo principles. Of course, there will be more to come. There will be more machine learning bots, for example, coming. But as we said in the beginning, we're not evaluating you on what you learned in sort of hacking an intelligent agent, but whether you understand the principles and that whether you understand or you learned a little bit better on how to do AI research. So how can you compare performance of two bots? What are the ingredients, the important ingredients of the intelligence that one of the engines that you built has, as opposed to another one, that make it function better, or that it might function worse, whatever. So this is exactly what we want you to do is, yeah, sorry? Sorry, say it again. That is a good question. I mean, you need to know and understand this for the exam as well, but these specific questions, the specific research questions, are something you have to answer about your own research idea. So everybody in every group will have a different research question. So you can't know the answers to these research questions from all the others, and we will not ask yours in the exam, because you won't have the answers at the beginning of week 4. You will still be in the middle of doing the research on your own research questions. So the exam questions will be far more sort of general. So your capabilities of doing research in AI is really something that will be evaluated in the report, in the final report. Yeah, I will give you some examples of papers that we consider well-written, good papers, and so forth. But in a while. But now it's time to sort of start thinking about what kind of things could we do research on. In a way, I think we have 4 types of knowledge, intelligent agents that we're going to build. Some of them have been almost provided, but anyway, you can use them anyway. So we have a min-max alpha beta one, which is probably only usable for phase 2. We have the perfect information Monte Carlo one, the PIMC, which is RDeep more or less, which can be already run now, which is provided more or less. We have the random bots. We can have a simple hill climbing bot, which will probably done almost nothing, like the random bot, or we have a bully bot. So there are already some things with a little bit of intelligent behavior. We hopefully at the end of this week will have a knowledge-based bots, which make these decisions on the strategies that you model in a rich first order or in a rich logical language. And next week, we'll build some different types of learning agents. And then the question is, you could compare different properties of a type of agent. So you could, for example, look at what is the impact of the sampling rate of the PIMC. So if instead of 100 rollouts per node, I do 1,000. It will probably take 10 times as long, but is it worth in terms of performance against the other? So you have to think about a performance measure. What is good? What is an improvement in performance? Winning the tournaments more often, winning against itself more often. So there are different ways of evaluating the quality of your agents. And we have provided the experiment and the tournament environment to help you come up with this evaluation criteria. You can look at different strategies within one type. So how much does it help to add more knowledge to your knowledge-based bot? So have more strategies, order these strategies, and so forth. But you can also sort of compare things. So what is the, do I ever have a chance of building a knowledge bot as opposed to a learning bot? Or if you apply the learning bot to the results, to the games that your knowledge-based bot has played, will it sort of get the same behavior after some training? Or improve? Will it be better? There are also things about you can think of the quality of your bots. So will they play better as opposed to other ones? Or will it, is the runtime something you find interesting to also look into? So is it worth looking 5 levels deeper? Is it worth doing at the end of your phase 2, doing a full min-max or a simple rollout? So these kind of things can be interesting to investigate. And these are all things, basically what makes this so interesting and exciting for me is that these are all research questions that I probably haven't seen before. And so I'm really looking forward to looking at these reports and seeing what kind of ideas you had, sort of what are interesting questions that come up in your head. So really showing that we do academic teaching here in the way of building up the curiosity and your urge to understand things rather than just solve them. And this is why we have these papers at the end as our evaluation. You have to write a paper, but I think you shouldn't start that much writing it now. It doesn't really make that much sense because you haven't really decided on the research question, and you can't really fix the research question until mid next week, I would say. But maybe it makes sense to already think about the background information. This is an example of how I usually think of structuring my papers. So the introduction gives a summary of the paper itself. So what is the research about? What is my contribution? And so forth. Then I need to really be very, very explicit and very clear about the research question. Formally, what is the problem I solve? What is the hypothesis that I prove or disprove? Then you have to describe how you do this, the experimental setup. I'm running on this computer, I'm running 5,000 experiments, giving this script with these two bots in order to answer my research questions. You describe the results, you interpret the results in your findings, and you conclude the paper by summarizing what is in the paper. And I will provide some example papers from the last years, and from some conferences which are sort of well written and good examples for doing this. So we still have 2 days on knowledge. Tomorrow I really want to show you how you can automate the decision procedures of is a formula satisfiable or not, and nicely set up as this advances in AI is. The way you solve the entailment problem or the satisfiability problem with Davis-Putnam is by search. And it's a clever way of doing search, so that's very nice. It's a depth-first, informed depth-first algorithm. It's really cool. So we look at this. What you should do is now start thinking about knowledge-intensive agents and how to implement them, how to model an interesting strategy. It might be that it takes us until tonight to publish the worksheet and the example bots. I've been working on this till very late last night, and Paul and Jeffrey are also working on this. Apologize for this delay, but there will be something tomorrow morning. I promise as much as I can. And then start playing around with the stuff to get a feeling for play tournaments against the different types of agents that you have. There are now many that work on the game, I think. Try to find out which one performs good and why and so forth. I will talk about tomorrow about Davis-Putnam and how this works and shortly discuss a second reasoning paradigm. And on Thursday we get into knowledge representation of uncertainty, where you are not really sure whether something holds or not, and approximations where you know more or less whether things are true or not. That was it for today. Have a good rest of the day and see you tomorrow.